going through, in this talk, I'm going to be going through what a epicycle theory actually is. I mean, I've touched on them in previous talks. I'll just go slightly more into the common sense maths of what epicycle theory is. I'll then look at neoclassical economics and show that compared to epicycle theory, which everyone uses as a watchword for a Baroque and unscientific theory, the epicycle theory was pretty good compared to neoclassical economics. And I may then go a bit on to dark matter. Okay. So, as I say, I've already touched on epicycle models, and they have a very bad reputation. They're seen as the classic example of avoiding falsification by adding complexity to a model, though there is considerable dispute as to whether that historically did happen. But at least they were a scientific model, certainly when compared to neoclassical economics. And they did make relatively precise predictions. And they're able to do that because the things that they were addressing, which is lunar, solar, planetary, apparent motions, are cyclical phenomena. And therefore, if you have a cyclical causal model, you can get reasonably good predictions from them. And they were at least potentially falsifiable. You could start to see things where the predictions were wrong. In contrast, neoclassical theory is much more Baroque than that. It makes only vague predictions and is inherently unfalsifiable, has been designed to be unfalsifiable. Whether that's deliberate, but the design is such that it is unfalsifiable. So let's recapitulate and say, what was the epicycle theory? What did it try to solve? How did it try to solve? How well did it solve it? And why was it rejected? And how does it relate to modern mathematical techniques? And we'll take the simplest example, which is just predicting the motion of the moon. It's something which most of us will have noticed, that on occasions, the moon seems abnormally large. You'll see a rising moon and think, God, that looks huge. Why does it look so huge? Now, part of that is to do with the human perceptual system, that it's thought that when we see something against a background of things we recognize, like trees or hills, we overestimate its angular size because we're familiar with those things. So that the moon, when seen against a background, appears to us to be bigger than when it's high up in the sky, and we can't compare it to anything except clouds whose size we've got no particular notion of. But it's not just that. The angular size of the moon does change. On some days, it really is bigger than others. And the second issue was that the moon doesn't appear to move at a steady rate across the sky. It only becomes apparent if you do very precise observations, but the number of degrees it traverses per day is not constant. Now, this is a scale drawing of the difference between a normal full moon and a so-called supermoon. It really does look bigger because at times it is visibly closer to us. It's 14% bigger when it's close to us. So that was known. This variation in the size of the moon was an observation that the ancient astronomers were aware of, and they knew it couldn't be going around the Earth in a perfect circle if it was sometimes larger and sometimes smaller. It had to be approaching and receding. And the speed of motion also varied. So it couldn't be something that was just rotating at an even rate around the Earth. Now, I'm taking the moon as the easiest example. Try to explain, at least they were right in having an Earth-centered geocentric approach for the moon. It does go around the Earth. So the complexities of heliocentric and geocentric models can be put to one side at the moment. Now, when the moon is at perigee, closest to us, it looks like a supermoon. When it's at apogee, it looks smaller. And this is quite different from whether it's a full moon or a non-full moon, because that shifts with the time of the year. So they knew that at apogee, it had to be further away than a circle, and at perigee, closer than the circle, than the radius of a circle. And that's sound scientific thought, or sound scientific deduction from observation. So it's not nonsense. It's something you can observe, and you come up with some theory to predict it. The epicycle theory, when applied to the moon, which is where it was first applied, gives an answer to both these problems. It allows the supermoon to be closer because the moon is assumed to have a main circle going around like this, and has a smaller circle whose center, an epicycle, whose center is on that larger. It is rotated into this position and can be seen to be closer to us. At apogee, it's in this position again and seems to be further away. So this rotation would have to be twice as fast as that rotation. And if we consider at perigee here, the relative rate of motion is going to be, according to the epicycle theory, faster, because the two circular components are adding, so it will be moving downwards here faster. At the other opposite phase, the two components subtract, and therefore its angular rate of motion is slower. So they could explain both things with respect to the moon with this epicycle theory. So it's not a bad theory. It's based on observations, and it explains some of the key features. And this kind of orbit could be calculated using rulers or ancient mechanical computers, as I've talked about before, with epicyclic gearing of various sorts. And these are modern epicyclic gearing. These are supposedly the gear wheels which represented the epicyclic motions of all the planets in the anti-theorem mechanism. Now, if you're just considering things from a Earth-centered viewpoint, all you have to account for are the apparent motions, the apparent angular motions in the sky. And you can, in fact, decompose any set of periodic angular motions into a set of epicycles. And I'll explain why. Why is it possible they could do that? And why is it that Newton's theory is actually better? Now, if we take a Newtonian model of the solar system or a planet, what do you need? You need, for each planet, you need a position in a plane, at least, an XY position in the plane at a given point in time. And you need initial velocities. And you need the mass of the planet, or planetary body. From that, those 5 numbers, Newton could calculate the next expected position. You only have to include the mass if you are wanting to have more than one planet and you want to look at the influence of one planet on another. If you take Ptolemy's theory, you need to have the phases of 2 cycles, the epicycle and deferent. You need the angular velocities of the epicycle and deferent. That's a misprint, should say deferent there. And you need 2 radiuses. Information economy in Newtonian as opposed to Ptolemaic physics. It's not a big information economy, but it's real and it is a simpler model. So let's look at neoclassical economics and say, how well does epicycle theory compare to that? This is Alfred Marshall, who is the founder of supply and demand theory, or at least the person who formalizes it into its standard form, which is still taught. And in the background here is the original supply and demand diagram in Marshall's 19th century textbook. So let's go back to what Newton was saying as the first rule of natural philosophy. He says that we are to admit no more causes of natural things than such as are both time and sufficient to explain their appearances. To this purpose, the philosophers say that nature does nothing in vain, and more is in vain when less will serve, for nature is pleased with simplicity and affects not the pomp of superfluous causes. So this is the keep it simple principle, the Occam's razor principle. So he is referring back to, when he says the philosophers say that, he's referring back to people like Occam. Leibniz is saying the same thing at the same time. Now, Leibniz gives a very good, interesting example. He says, let us assume, for example, that someone jots down a number of points at random on a piece of paper, as do those who practice the ridiculous art of geomancy. In other words, divining. I maintain that it is possible to find a geometric line whose motion is constant and uniform, following a certain rule, such that this line passes through all the points in the same order in which the hand jotted them down. But he insisted that such a line could not be the basis of a law because it'll end up being too complicated. A scientific law must have some kind of economy. It must perform some kind of data compression. It must have fewer parameters or free variables than the observations it has to account for. And the more data compression you can do, the better it is, the better the theory. This is a very basic point. Now, let's evaluate Leibniz's claim, or carry out a demonstration of Leibniz's claim. He says that given any data points on a graph, on graph paper, he could come up with a formula for a curve which went through the points. And I'm going to try that using the world oil market data. I just at random chose some readily obtainable economic data. So what we have here is a table, the years, the output of oil in millions of barrels a day, and this was the price of oil. And I took the 1st of January or some similar standard date for each year to model this. The data is far more bulky than that, in that you can get data for every day. So I took standard subset there of these days. The final column is the price per barrel of oil. Now, if I plot them, there seems to be some sort of vague curve, but it looks, and at another level, you could say, well, there might be some kind of curve there that oil price seems to peak at around 86 million barrels a day, and then falls off if the amount of oil produced is less, or falls off if the amount of oil is produced is more. Neither of those, of course, correspond to Marshall's theory, but Leibniz said something stronger than that. He said, if you give me a set of points, I can come up with a mathematical formula which will go exactly through all of them. Now, I don't know what formula Leibniz would have used or what approach he would use. I suspect that given that he's a co-discoverer of the calculus, he would have used a polynomial function with a degree equal to the number of points you want to go through. That's one way of doing it. I'm going to use another way, which is a Ptolemaic approach to fitting the data. It took me a little while, but it's not that hard to come up with a discrete cosine series which exactly fits the data. So these are the points, and I've drawn a curve which exactly goes through all of them. But it's a rather arcane formula. There's some sense to it. I'll explain it by steps. We're roughly interested in the period from, the volume of oil from 80 million barrels to a bit over 90. So let's squash that down and express it as a cycle. In going from 80 to 90, we'll treat that as one complete cycle. So I say Q minus 80 and divide it by 10. So that would be Q minus 80 divided by 10. So from 80 to 90 would give us 1. And I multiply it by pi to say that is a complete cycle. So dealing with cyclical phenomena, that's why I multiply by pi. I then fit a set of cosine curves that will exactly go through this. I'm not going to go through how I estimated the parameters of the cosine curves, but these are done very regularly. I say some offset, some starting phase, plus theta, plus 2 theta, plus 3 theta, 4 theta, etc. So I have multiples of theta going across there. Why do I do that? It's because you know that for integer multiples of theta, the cosines for a complete cycle will be orthogonal to one another. That's to say, their inner product will be 0. And they correspond to orthogonal axes in a particular space. If you know that, it's then a matter of taking a vector, which we have here, and expressing that vector in this new basis space of the cosine curves. So that's analogous to the problem we were talking about last time of taking a sighting of a ship and rotating a frame of reference and getting the coordinates in the new frame of reference. So probably was possible that Leibniz knew how to do this, because after all, in a way, Ptolemy was doing it. But it was only formalized by Fourier quite a lot later in the 19th century. So there are other orthogonal basis spaces which can be used, and I gave the example of a polynomial of the right degree. Remember what a cosine means. What you have is a cycle on this circle here, And you can project off that the horizontal or the vertical positions. And if you project the horizontal positions, you get the cosine curve. If you project the vertical positions, you get the sine curve. So what they're just expressing is position in one dimension generated by a rotating body. The projection onto the X or the Y axis of the a body rotating in a uniform circular motion. Now, when you take that into account, it becomes evident that a model of that sort is going to be very good for predicting the motion of something going around the Earth. And if you consider what the original epicyclic model of the lunar motion was, well, essentially you have two circles. You have the deferent and epicycle, and you're projecting components of those. So if we take one, the red curve is the epicycle component, the blue curve, the deferent component, and the yellow curve is the sum. So what was Ptolemy doing? He was adding up cosine functions in just the same way as I've added up cosine functions to model world oil prices. But if I go back, it's clear that this is a nonsense theory of world oil prices. It fits it perfectly, but it's complete nonsense. And it's an illustration that of what Leibniz was saying, is you can always come up with the exact maths formula which fits the data. But if it's an arcane and elaborate formula, it's not a natural law. Sorry, I've explained this already when I went through. The question is how efficient is this theory? What we've got is a general rule. This is replicated rule here, because I'm saying cosine 2 plus theta, 2 plus 2 theta, 2 plus 3 theta. So that's a general rule. Let's ignore that part. I have to fit it with parameters. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 constants. Plus there's another couple of constants in my definition of theta. So maybe 10 to 12 constants. And how many data points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 data points, 10 constants in my formula. Does that constitute a natural law? No, because there's no economy of data. I'm using as many constants as there are observations. In some way, okay, you say maybe there is some economy of data, because each of these observations has two components. It's got an X and Y component. So maybe you could say there were 20 numbers in my original table. If we go back to the original table, ignore the years, well, there are 20 numbers in that table. The formula has now fitted that with 10 or 12 constants. So perhaps you can say it's an efficient formula. But is it a law? Obviously not. It's far too long and complicated. No one's going to suggest that that's a plausible law for what regulates world oil prices. Now let's look at Marshall. What's the ideological background to Marshall? Well, Marshall's working in the late 19th century, a period when a socialist movement, which followed the labor theory of value, was becoming significant, and the labor value theory of the classical British economists was potentially politically problematic at that point. So he replaced it with one which the market price is given by the equilibrium intersection of supply and demand curves. And this is what all economics students are taught in Economics 101, and everyone is supposed to believe this. And it's been the standard treatment really since the end of the 19th century. It took a little while to establish itself, but by the 20th century, it was a standard treatment. If supply and demand explain equilibrium prices, then we can dispense with the classical theory, because in the classical theory, supply and demand was recognized. I mean, Smith, Ricardo, and Marx all knew that supply and demand operated, but they were seen just as disturbing factors on an underlying law value, which was determined by the labor time necessary to make things. If you can make what were previously disturbing factors the center of your theory, you can disregard the labor theory of value. It was no longer necessary to explain what the classical economists considered to be the center of gravity of prices. Instead, you have something that does better than that. You explain the individual prices, not just their center of gravity, which from the neoclassical point of view is a much better theory, because it gives you a precise answer rather than saying, oh, well, we've got a general estimate and there's disturbing factors. It appears to be more precise. So in the theory, the actual equilibrium point at any given day is given by an intersection of two curves on a graph which the x-axis is quantity, the y-axis is price or dollars, and the two curves are called the D and S curve. This is the demand curve, and this is the supply curve. And if you're not at the equilibrium, if the price is too high, there is a surplus, and the surplus is being produced more than is demanded, and the price will fall to the equilibrium point. If you're below the equilibrium point, the amount demanded here is greater than the amount supplied, and you move to the equilibrium point. So it has the appearance of giving not only a precise definition of price, but explaining why actual prices gravitate towards that. But let's look at this from Leibniz's point of view. How much information is required for these curves, for the supply and demand curves? Normally, you just see them drawn as curves like that, just colored curves or dotted curves. But when Marshall published his original book, he actually drew it on graph paper. So you can actually see the points where in his examples, the curve is for units of goods. At 4 units of goods, the price, he says, is 5. At 10 units of goods, the price is 9. So you can read that off. And because you can see it's a curve, it's clearly at least a second order. Sorry, I'm looking at the demand curve. It's at least a second order polynomial, because if it was not a second order polynomial, it would be a straight line. So it must have at least 3 parameters, A, B, and C. And since he gives actual points, you can solve this and say what curve would give, what polynomial function would give that curve. So that would give it. Where does he get this formula with the 3 constants? I mean, my oil formula was arcane. This is another odd formula with 3 constants. Well, he just makes it up. This isn't based on any real observations. He is just saying, I'll draw a curve and that'll explain things. He plays let's suppose, but he never writes it down explicitly in mathematical form. nor do lecturers in first-year economics at universities now ever write it down in mathematical form. They draw it geometrically. They draw it by hand on the blackboard. The problem is, if you actually write it down in mathematical form, it immediately appears to be completely arbitrary, just as my polynomial function for, my cosine function for oil prices was obviously completely arbitrary. But it gets worse. If we look at his supply curve, it's got two inflection points, one there and one there. So it must be at least a third degree polynomial. I'm not going to derive the values for this from the graph, but you can see for this, he has two curves, the demand curve, the supply curve, and the equilibrium is given where demand equals supply. So he claims that his maths enables him to simultaneously to determine both the price and the quantity that will be sold. But in order to do that, he has 1, 2, 3, 4, 5, 6, 7 constants. Now that's not apparent because it's presented to the students just as a drawing. 7 constants to explain one price and one quantity. So he has 5 more constants in his model than what he's explaining. 7 free variables. Two curves with 7 parameters to explain 2 numbers, the supply price pair. In his example, 10 is a supply and price is 9. So where is the information economy here? This surely is, what Leibniz was calling the ridiculous art of geomancy, dotting things and then drawing lines through them. It's a 250% redundancy. Now, people talk of the epicycle theory as being redundant, but it only had a 20% redundancy compared to Newton. Here in supply and demand theory, you have an enormous redundancy, and they're completely imaginary. No one has ever been able to measure simultaneously a supply and demand curve. We know that the epicycle theory is wrong because you can actually use Newtonian dynamics to fly to the moon and land on it. If you used epicycle theory, you'd land at the wrong place. Now, Leibniz says if you want to have a mathematical rule that it's a law of nature, it should have as few free variables as possible. And if we take Newton's law of gravitation, he's saying the force law is equal to just taking the force, change in the force which produces a change in momentum. It's the mass of body 1, the mass of body 2, and the distance between them. And it's equivalent to the gravitational constant, the product of 2 masses divided by the square of the distance. So that's a nice simple formula. It has 3 explicit parameters: the masses of the 2 bodies and their distance. Those can be obtained from observation, or can be estimated at least. It only has 1 free variable, g, because these two, the masses of the 2 bodies are applied in every single instance, but it has 1 free variable, which is a free variable of the whole theory. But that can be filled in by experimental constant, the universal gravitational constant. That can be filled in by actual measurement. The measurement was done in 1774 using Mount Schiehallion in Scotland. The astronomer royal, Maskelyne, did a series of observations on an observatory on the side of the mountain, in which he observed the zenith position of stars and observed a deflection of a plumb line due to the mass of the mountain. And from this, he was able to determine what the gravitational constant must be. They had to do a lot of other things. They had to do a very precise survey of the mountain in order to work out its volume. And having worked out its volume and measured the density of the rock that was being used and measured the deflection of the plumb line, they could come up with an estimate of G. There's been some controversy over whether this was feasible, but and whether you could get such good results. But I think the latter-day skeptics have ignored the great care that the 18th century astronomers went to get their result. On the other hand, in the case of neoclassical theory, it's absolutely impossible to estimate the free variables because these are hypothetical situations on the supply and demand curve. The supply curve is the amount that would be supplied if the price was different. And the demand curve is the amount that would be demanded if the price was different. But all you've actually got at any one time is an observation that today, so many million barrels of oil were produced and their price was such and such. That there were 81.3 million barrels of oil produced and the price was $51 per barrel. For that observation, there's an infinity of different curves which could run through that and make that point. So the actual curves are just figments of the imagination. They're drawn to have a shape which seems plausible to generate a nice intersection. But why should it be that curve and not this curve? Well, you could say, well, you observe them over time. You observe the supply curve by looking at different dates and see what the prices were on those dates when different quantities were supplied. But it's only a scientific abstraction if you've got an observational procedure for estimating the function. And to do that, you need to have as many observations as there are parameters on your curve. So in order to have a supply curve, which is a second order polynomial, you need at least 3 observations. But it's not observational because according to neoclassical economics, any change in price is produced by a shift of one of the curves. So a price can be explained in terms of the supply curve shifting in the first case, or in the demand curve shifting. According to economic theory, each price change requires at least one of the curves has shifted. And if we knew which one had shifted, then we might be able to estimate the other one, but we could never estimate the one that had shifted. But since both of them may have shifted, we're none the wiser. If you look at the actual data I started off with, what curves and shifts of them must have produced this? You have, any economist can, if he wants, draw 20 curves which intersect at these 10 points to give us the real observations. And no one can disprove these hypothetical curves. But the curves are like fairies or angels. People can assert that everyone has a guardian angel, but they're invisible, so no one can see them. And no one can disprove that you have a guardian angel. But none of that is science. And these curves, since they are in principle unestimatable, are like fairies. My joke theory required 12 parameters to fit the data. Samuelson's wandering curve account, I tried to use the minimum number of curves to go through, drawn by hand. And this required a very implausible curve to go through the whole lot of it. But to do that, I would require around 35 parameters to fit that. And that's me assuming that in this case, the supply curve was constant and we got changes in the demand curve. In that case, we got a change in the supply curve. Then we got a change in the supply curve again, but you have to assume a very wiggly demand curve to account for that. It's pure mysticism, really. It's like an old style black magic seance where the magician draws pentagrams on the floor to impress the apprentices. The students are being impressed by these curves which the lecturer is drawing, but the curves are just curves. They're just curves on a blackboard. They're not theories. You have to accept some things are just random. What is something random? Well, random data is data whose mathematical description is more complex than the data itself. You have to accept that economies are stochastic systems. And as such, they're subject to random noise. And if you construct a theory like neoclassical economics that gives no information efficiency, it's just a higher form of superstition. And you don't get this just in economics. In other sciences, people are much more rigorous. They're not as completely mystical as in economics, but you do get controversies where the efficiency of a theory is genuinely under dispute at the forefront of a science. So it's arguable, it certainly is argued, let's say, it is argued that cosmology has the same problem with dark matter, that they have a theory with too many free variables that could be made to fit any data. In the case of neoclassical economics, you can always invent a pair of supply and demand curves to explain any price. The redundancy is not as bad as that in current cosmology, but there is a argument that that's what's happening. Why do people credit the existence of cold dark matter? Well, it comes down to observations of the orbital velocities of stars in galaxies. According to Newton's laws of motion, the rotational velocity of something further away from the center of mass is going to be slower than something close to the center of mass, so that the rotational velocity of the Earth is much faster than that of Saturn, which is further away from the sun. But whilst the Newtonian law fits very well the solar system, when you look at the whole galaxy or other galaxies, it doesn't fit it. The orbital velocities actually appear to increase with greater distance rather than fall off. If you take a galaxy and estimate its mass in a given volume by the, or the center of mass by the visible stars, and use this to compute the expected orbital velocity of the stars around the center, you get the lower curve here. The actual observation is much faster rates of rotation. So there's a discrepancy here. Either there's a lot of matter you can't see, and the mass, this unseen mass, forces things to rotate faster than the mass you can see. That's the generally accepted theories still. Or Newton's equations for acceleration are wrong when dealing with very small accelerations. And that's what's called modified Newtonian dynamics, or MOND theory. In MOND, Newton's law is replaced by a law: force equals mass times acceleration plus 1 plus some small constant, a new fundamental constant, over the axial acceleration. And Milgram introduces one new fundamental constant into the laws of motion. And basically the effect of this is to extend gravitational force further than Newton said it would, independent of radius, which is what we observe for big distances and small accelerations. Now, if we take a particular galaxy, the MOND theory has the prediction on the right-hand side there. The dots are the observed velocities at given radiuses from the center. The standard theory explains this by 3 components: the observed visible stars, some invisible dark matter, and some inferred gas. And these 3 components are added together to derive the observation. The problem is that since you can't see the invisible dark matter, and you can't see the inferred gas, the astronomers are free to draw these in such a way as to fit the observations, which is not far off what the economists do. The difference is that MOND explains it only in terms of what can be observed, whereas dark matter theory explains it in terms of inferred gas plus invisible dark particles. And it's arbitrarily precise, since you can't see the dark matter, you're therefore free to posit any distribution of dark matter you want in order to account for the observed motions. And for any observed motion, you can infer a pattern of invisible matter. It gives them almost as much freedom as the economists with their supply and demand curves. Now, it does, however, make predictions. If there is matter there, it should be made up of particles in some form, weakly interacting massive particles. So people have proposed experiments to detect the dark matter, that they have cylinders of liquid xenon with photodetectors, and the idea is if one of these dark matter particles, which normally is assumed to only interact normally by the gravitational force, but is assumed it must have some kind of other interaction with matter. And if it hit one of these dark matter particles, hits a xenon atom, you'll see a flash and detect it. Well, no one has ever found them. And it's not as if there hasn't been a history of this. Newton's theory was very successful in that anomalies in the orbit of Saturn led Leverrier to predict the existence of an unobserved mass, which was later observed as Neptune. So, assuming something dark and unobserved, disturbing the orbit of Saturn, was a reasonable hypothesis given Newtonian theory. You apply it, it says, look in this position, you look in this position and you see Neptune. So that seems to confirm Newton. It also confirms the method of accounting for anomalies in terms of unobserved objects, or as yet unobserved objects. Next, there's an anomaly in the orbit of Mercury. And in the 19th century, it was taken as almost certain that there was another planet closer to the sun, which was even given the name Vulcan, which accounted for the anomaly of the orbit of Mercury. But like dark matter, no one ever managed to observe this other planet. Obviously, the brightness of the sun is a problem, but you should at least be able to observe it transiting the sun. So what you ended up as an explanation for that, though, was actually Einstein's modified theory of gravitation. And he was predicting that among the predictions of it were that the gravitational effects become significant where, general relativity becomes significant where gravitational effects are very strong, as in close to the sun. And this leads to a different orbital behavior of Mercury, which is close to the sun. And it's testable by saying, okay, it will bend the light rays from stars as they pass close to the sun. You can't see that normally, but in an eclipse, you can see the position of stars which would normally be dazzled. You would normally be dazzled trying to observe them looking at the sun. And in 1918, I took photographs at a time of eclipse and superimposed these on photographs taken under normal circumstances, and was able to show that, yes, stars close to the sun were shifted in their apparent position. So what that indicates is that when you have an anomaly like this, you either have to choose to infer something within the context of the existing theory to explain it, or you have to say you're going to modify your theory. And this is a live controversy in cosmology at the moment, whether or not dark matter theory is right, or whether or not the Mon theory is right. On philosophical grounds, the Mon theory appears right because it's a simpler theory. On the other hand, there's a huge established set of assumptions about dark matter, and it's taking time to displace it. And it's conceivable there will be definitive observations which I will stop now. I think I've slightly underestimated my time, but that will do.